events and like how to find out whether or not events are independent. So let's start by talking about some very straightforward probabilities. If we flip a fair coin, what is the probability that it lands heads up? 50% or like 0.5, right? 0.5. Let's try to be consistent and just do it as decimals. Okay. If you roll a standard 6-sided number cube, what is the probability that it shows a 5? Well, that would be like 1 out of 6 possible outcomes. So what is that?
1 out of 6.
Yes. Okay. So let's say 0.167. 0.167. All right. What is the sample space for flipping a coin and rolling a number cube? So when we write out a sample space, not right now, man. I already told you what to do. Nope.
Look at them. That's like nothing.
Nope. Not right now. Okay, so this is how we write out a sample space with all the possible combinations. All right. So we can either start with a heads or a tails, right? And then after we roll either heads or tails, we can get 1, 2, 3, 4, 5, or 6. So we can get heads and a 1, heads and a 2, heads and a 3, heads and a 4, heads and a 5. Okay, I did not get myself enough space. So I'm sorry that if you were writing as big as I was.
You're doing great.
You have to do the tails too.
Yeah, you do.
All right.
That's why that was the problem. I was going to make it if it was just heads. Okay, so now we're going to use our sample space that we created. How many total events are in our sample space? Yeah.
12.
Yeah, okay. So use the sample space above to determine the probability that the coin lands heads up and the number cube shows a 5. So we want heads up and a 5. 1 out of 12. As a decimal, that would be 1 divided by 12. I'm getting 0.083. Guys, right now we are going to practice this notation just so that I set a good example. So that's the probability of landing heads up and the getting a 5. So what is the symbol for and?
And.
Intersection.
The intersection, the upside down U. Okay. And a 5. Okay. Ideally, I would have written that first, but that's not the way it happened. So we'll fix it retroactively. All right, let's look at the next part. Look at the individual probabilities of having heads showing on the coin. Probability of heads and of having a 5 show on the number cube. Probability of 5. How could you use probability of heads and probability of 5 to determine the probability of the coin showing heads and the number cube showing a 5? Okay, so I'm glad that we wrote this 1 as a 1 over 12. Can we, up here at the top, rewrite this just off to the side as 1 over 2? And what was this one? 1 over 6. Do you notice anything special about this one, and this one?
An even number.
Okay, they're even. They're multiples of 2. That's kind of the same thing as even.
You can multiply 2 and 6 to get
Divisible by 2.
Okay, you probably didn't even hear what she said over there. Will you say it again, please?
Oh, you can multiply 2 and 6 to get 12.
Oh.
Wow.
Do you guys see it?
That's crazy.
Do you see it?
Yeah.
Okay, so our girl Elena just figured out the multiplication rule for independence. Let's give her a round of applause. Okay, so we can multiply the probability of getting heads with the probability of getting a 5 to equal the probability of getting heads and a 5. So if we have 1/2 times 1/6, that is going to give us 1 over 12. Everybody see it?
Yes.
You can't see it? You need to be closer? Do you need to be closer? Okay. Okay, think about the 2 events from questions 1 through 4. Does the outcome of one event affect the outcome of the other event? So can I change what happens on the number cube by flipping my coin? Is one dependent on the other? No. They are independent. Feel free to either use the exclamation point or not use it.
I'm not.
Okay, one does not have any effect on the other if they are independent. Right. Okay, so for independent events, the product of two events, would you put an apostrophe after that S because it's possessive? Individual probabilities is equal to their joint probability. Okay, remember that joint means and. Intersection. The outcome of one event has no effect on the outcome of other events. Okay, we can prove independent events with the multiplication property of independence. Two events A and B are independent if this is not a drill. Okay. All right, now we're going to talk about dependent events. Okay, these are ones where the outcome of one event has an effect on the outcomes of other events.
Damn, dude, you good? Yeah, I'm good. Allergies.
Use the little probability test to like actually test them and see if we're right. Okay, so what is the probability of rolling an even number on a dice cube?
4 out of 6.
Okay, 4 out of 6. Okay, what about, wait, what? Let's try 3 out of 6.
Okay.
All right. And what about rolling a 3?
1 out of 6.
I said 5.
1 out of 6.
1 out of 6. Okay, so that is equal to what?
3, 12.
Okay, 3 out of 12, which reduces to, oh no, it's not 3 out of 12.
36.
3 out of 36.
Hey, I got mine.
Okay, can we, okay. Okay, can we reduce this? 1 out of 12, thank you. Okay, so let's see what their joint probability is. What is the probability of rolling even and getting a 3 on a single cube?
What? Like, oh, yeah, twice?
No, at the same time.
It's impossible.
So the probability is,
Like, you can't, 3 is not even number, right?
the probability is
0.
0. So are these independent?
I don't know.
Is 1/12 the same as 0?
No.
No. So are these independent?
No.
No, they're dependent. Okay, what about picking a marble out of a bag, not putting it back, and then picking another marble out of the bag? They don't tell us enough information about how many marbles are in the bag, so we're just gonna have to like think about it. So instead of marbles, let's do markers because I've got some colored markers up here. Okay, so would you please pick a marker out? What is the probability right now that she picks an orange marker?
1 out of
1 out of 6. Okay, would you pick any marker? Okay, so now what is the probability of her picking an orange marker? 1 out of 5, because she didn't put that one back.
Right.
Everybody okay with that?
Yes.
So because of the words without replacement, that makes it dependent. Thank you very much. Okay, so those were dependent. Not replacing it, dependent. Okay, what about drawing a heart and a face card? Okay, so this one we can do the math on again. So the probability of drawing a heart would be 1 out of how many? Okay, so 13 out of 52? Or 1 out of 4, right? Okay, and then what about drawing a face card? So there's 3 face cards and 4 suits. I'm getting 12 out of 52.
Yeah.
That's fine. Okay. Can I show you guys a trick for multiplying this where you don't have to reduce so much at the end? Do you see that inside the 12 there's a 3 and a 4? Okay, do you see that I have a 4 on top and a 4 on bottom? They cancel. So now it's just 3 over 52. You like that trick?
Yeah.
No?
I love it.
You know, like how we have an X on and a Y on top and an X on bottom, and the X's cancel. It's just like that. Isn't that cute? Cute little tricky poo. All right. Now, so that's like their probabilities multiplied together. Now we have to find their joint probability. So this is finding the probability of a heart and a face. So the probability of a heart and a face. So how many heart faces are there? Okay, guys, we're gonna come back to that one. My brain is having a brain fart. We're gonna have to come back to it because it's not turning out the way that I thought it was going to, and I feel like I did something wrong, but I don't know what it is right now. All right, so we're going to use this cute little. Okay, turning the page is not an invitation to have like an entire discussion. Okay. I don't know, guys. Okay, so relative frequency, we have this contingency table and we have to answer these questions. So we have to consider the events has one pet and flying. Has one pet and flying. Okay, are these independent, do you think? I don't know about you guys, but I can't really, I don't know that I can really tell right now just by looking at it. So I would say it's kind of hard to say, but what do we think? What's your gut say?
Independent.
Maybe independent, we don't really know. Maybe independent. Hard to say. Okay, so this is why we need the test, because some things it's obvious, like we didn't even have to know how many marbles were in the bag to know that if we don't replace the marbles that we're drawing out of the bag, it's dependent, right? Like we didn't even need to know any numbers, we could just tell. But for this situation, like we're gonna have to do a test. So, we're going to use the multiplication property of independence to determine whether or not the events has one pet and flying are independent or dependent. So we need to do probability. This is how I like to think of it. Probability of one pet times probability of flying. We want to know, is that equal to, don't forget the question mark above the equals because we don't know if it's equal or not yet. Is that equal to their joint probability? Probability of one pet and with intersection, flying. Guys, I'm just going to get this packet so that I can see the numbers and move the screen up. Okay, so what is the probability of having one pet? Over on the far right.
0.35.
Okay, 0.35. Okay, what about the probability of flying down at the bottom?
Same thing.
Okay. Guys, I'm going to put these in parentheses so that my dot doesn't look like another decimal point. Okay, and then what is the probability of the intersection of having one pet and flying? So the intersection is this right here. Pew, pew, pew. Okay,
Oh, shoot.
so that was 0.075. So we just have to multiply these together and see if we get that. So 0.35 times 0.35. I'm getting 0.1225. 0.1225 does not equal 0.075. So what can we conclude? Correct.
I didn't say that.
Therefore,
No, you didn't. Not real.
dependent. Actually, Kennedy did say dependent, but then she changed her mind. She got swayed. Okay, what does it mean in the context of this problem that the events are not independent? What does it mean that they are not independent?
They rely on each other.
Uh-huh.
Toodles understand.
What?
And depends on the other one.
Okay, so what do you think? I feel like there's a way that I want to say this, but right now I'm struggling to find it. Okay, so I think we can just say something like having one pet changes the likelihood that they want to fly, and vice versa. So changes the likelihood that the person picked would have selected flying. And vice versa. We could also say that, whoops, that's vice versa. Vice versa. We could also say selecting flying changes the likelihood that someone has one pet, right? We could say it either way. Any questions about that one? Okay, Toodles has a bag with 12 marbles in it. We got 4 blue marbles, 5 orange marbles, 1 purple marble, and 2 red marbles. We're gonna find the probability of Toodles reaching in the bag and selecting a red marble, then a purple marble without replacement. Okay, first we're gonna pick a red marble. How many bags are in the marble bag? 12. How many red marbles are there? 2. Okay. Now, are we putting the marble back? No. So the second time we do this, how many marbles are in the bag? 11. Okay, now what are the odds of getting a purple marble? 1. Okay, now, if we want to do a little bit of canceling before we multiply, do you see that there is a 2 in the 12?
Yeah.
So 12 is 2 times 6. Cancel the 2's. Guys, I swear this will make you fast at multiplying stuff. Okay, so now we have 1 over 66. And we don't have to reduce. Let's write it as a decimal also, so we can practice that. 1 divided by 66. I'm getting 0.105. 0.015. What did I say? 0.015. Okay, find the probability of Toodles reaching in the bag and pulling out a blue marble, tossing it back in the bag, and selecting an orange marble. Okay, so how many marbles in the bag to start out with? 12. How many blue marbles? 4. Okay, how many marbles in the bag the second time? Huh? Careful, you put it back. Okay, if he tosses it back, he's got 12 marbles again. How many of those are orange? 5. Okay, we can do our little trick again. There's a 4 in that 12.
1 over 3.
So yeah, that's a 1 over 3. Okay, so 1 times 5 is 5. 3 times 12 is 36. We can also divide it on the calculator. 0.139. Okay, find the probability of Toodles reaching in the bag and selecting a red marble, then a blue marble, and another blue marble without putting any back. All right, I'm going to need your guys' help on this because I can't see how many marbles there are anymore. So, first time he reaches in the bag, we're starting with 12 marbles. How many red? 2. And then the second time, we're down to 11 marbles. How many blue marbles? 4. Okay, and then third time, third time, how many marbles will be in the bag? 10. But we have to allow for the possibility that we already took one of the blue marbles out. So how many blue marbles? 3. Okay, so it goes from 4 to 3. Everybody okay with that? Okay. So inside of these numbers are some really great factors. Here in the 12, we have a 3 times a 4. You see I have a 4 up here and a 3 up here. Okay, inside the 10 is a 2 times a 5 that cancels my 2's. So the only thing left in my numerator is a cute little 1. What's in my denominator? And a 5. So 5 times 11, 55, and I didn't have to reduce anything. It's pretty slick. It's pretty slick. That's how you get through upper level math classes without knowing your times tables. I'm telling you all my secrets. All right, 1 out of 55. 0.018. Okay. 0.018. Okay, so this one was without replacement. And this one was also without replacement. So when did we have to change the denominators? Right, when we didn't put the marbles back, because we're not picking out of the same number of marbles. Okay? If we're putting the marble back, then we just leave the denominator because we're always picking out of the same number of marbles. Okay, we're going to do this part tomorrow.